Yes!
Here we go.
Thermal systems, thermal strength on Intel i7 6600U graphics performance. Let's welcome the presenter.
Okay, good afternoon. First of all, I want to thank the chair for the introduction. I'm glad to be here to present you our research on the impact of prolonged thermal stress on Intel i7 6600U graphics performance. So for this research, we worked on a commercial off-the-shelf processor. It means this is a commercial component which is used for consumer electronics, so it's a component that you can find inside your laptops or in your home computers. So it's not a specialized test chip or some development kit or something like that. It's completely commercial. So the interesting part of this research, which motivates us to work with it, is that usually when accelerated aging processes or research are performed, the factor of the thermal stretch which comes from the CPU itself is not taken into consideration. Usually an external heat is applied or external voltage in order to create this thermal stress. However, in normal consumer electronics, we have the problem of dust, which is behaves like what we see in the photo. So it blocks the air vents, and this way the cooling capabilities of the cooling system is reduced, resulting to overheating. It doesn't matter if we are speaking about some data center which is operating 100% all the time, or if it's about our home computer, desktop, or a laptop. So in order to reach the real world conditions, we have a real world stress investigation, which is focused on a standard Dell laptop, which was operating at 100% for some weeks. We didn't apply any external heat or any artificial voltage, so the system was operating within the normal world conditions as it's designed to be operating. By doing some modification of the fan, which we'll see later, we also reached the dusty heatsink phenomenon, which we saw in the previous photo. So this way we have a closer alignment with real use scenarios than other approaches which rely on external factors which are not normal in real life conditions. So in order to mimic the real world conditions, we did a modification on the cooling system. So on the left side we see a laptop heatsink with its fan. This is how maybe your laptops are also out inside, some of them maybe. So what is happening is that dust is being collected on the fan, and then this dust moves onto the air vents, blocking them. So when the fan is spinning, the air can't go through these air vents, and then it means that heat cannot be transferred through the copper part from the CPU to the environment. And this means that the CPU is overheating. So in order to mimic this situation, on the right side we see the fan, the cooling system of this Dell laptop. So of course we cleaned it properly and we replaced the thermal interface materials. But we also installed 3 resistors in line with the fan. And this way the fan speed was reduced to a certain level, which level means that the CPU was operating at 95 to 97 degrees. We chose this temperature not accidentally. It's the temperature after which the CPU would start to do the overthrottling, thermal throttling process, which means that the performance and the frequency would be reduced, so we would not be able to measure the performance, which is the purpose of this experiment. So this is the maximum temperature that the CPU would be operating at full performance. So in order to to evaluate the aging effect of the experiment, we used a literature study which states that as the component is aging, the EMC emissions are being reduced. So during the whole time of the experiment, an oscilloscope was connected on the laptop, on the CPU, measuring this emissions. And we were recording the numbers daily or even more often. In order to measure the EMC, we used the 1 ohm probe method, which is defined by the standard IEEE 61967/4. So in the photo we can see the practical application of this method. Practically a cable connects the bottom part of the ground of the CPU through a resistor 49 ohm to the ground of the power source. And then we use an 1 ohm resistor to connect the probe to the oscilloscope in order to measure the EMC emissions. But the critical part is to measure the performance, to verify the performance of the CPU, and this was done through commercial benchmarks software. So we used a series of different software. These are normal program software which are used usually by computer enthusiasts who play these games, and in order to evaluate how strong, let's say, is their computer. The interesting thing with this benchmark is that each program measures about the same things, but also in a bit different way. So the scores are quite different to each other, so we can't compare scores between different benchmarks. Each benchmark must be examined by itself, so we check the score in the beginning of the testing and through the process, but we can't compare this score with the score from another benchmark. So here we enter the Ancani because we see the results of the scores of these benchmarks, and with red we see some values which are not expected the way they should be. They're not measured the way they were expected to be, because we would expect that when the component is aging, the performance should be reduced, but some values are increased. But first of all, I would like to clarify what day 1 and day 21 means. Day 1 is the beginning of the experiment, so the CPU hasn't gone through accelerated aging yet or any thermal stressing. Day 21 is after 3 weeks that the CPU was operating at full load, so at 100%, but without any modifications to the cooling system. So the temperature of the CPU was within the limits that the manufacturer has designed it to be. Just the operation was at 100%. And after the 21st day, for around 8 or 9 days, the CPU was operating again at 100%, but with its cooling system modified, so the operational temperature was 95 to 97 degrees. And the experiment finished at the failing point, which means that the CPU started to give signs of failure, which is like the system became unstable or would not be able to load the operating system sometimes, or just freeze. So these are indications that something is failing in the system. We confirmed that the failing was related to the CPU by replacing the CPU with a brand new one, on which we performed the reballing process, because the soldering ports are a very common reason why these components also fail. So after we installed the new CPU, the computer was operating normally, so we could confirm that it was related to the CPU. This problem was related to the CPU. Okay. So in this table we see some strange numbers. We see that some numbers, some scores are increased on 21st day, and some scores are reduced, and especially in the failing point we have some clear evidence that the CPU performance has started to be decreased. So this is quite strange, and also proves how complicated is this circuit. But we have to understand exactly why some scores were increased in the middle of the process. So With the new CPU that we installed, we did one more testing. We applied new thermal materials, actually phase change thermal materials on the CPU. And we did one test using Intel software, which measures temperature, CPU utilization, and max code frequency. And we performed again the second test, the same test, after a couple of days of usage, when the CPU went through some thermal signals. So the phase change material started to be applied by itself, let's say, better. So this here we see the reason why we had improved in the previous testing, because the package temperature in the first test was a little bit higher than in the second test, and this resulted in a little bit increased Markov for frequency in the second test, which means that the temperature of the CPU was a little bit higher, preventing him to operate in higher frequency. This test goes through. So this increase was because of the phase change material. As we said, the EMC was always measured with the experiment, and we expected to decrease, and it did decrease. So the first time decreased quite slowly, and then during the second part of the experiment, it decreased very fast until it reached near 20% of the original measurement. So using the exponential decay model, we can quantify the aging rate of the component based on the measured EMC. We had the luxury to have this laptop in our workshop for a few years, so we knew exactly its operation time. And by installing a new CPU, we were able to establish the starting point of the EMC and the finishing point in the failure, during the failure. And through this, we calculated the case tables for normal operation and for stress conditions. And as we see in this table, for normal operation, we would expect that the component would last for almost 1 century, while under thermal stress condition would be near a bit more than 1 year. These numbers comply with what we know from our workshop experience. So, of course, 1 century you don't have to measure the normal condition, but there are computers running for more than 40 years. But we have a lot of failures in laptops near 3 years, which is related to this dust concentration in the heat sink. So the conclusions from this work is that high demand workloads can lead to measurable EMC decline in performances, and exponential models allow the estimation of time to failure under various conditions. These findings can enhance understanding of CPU aging, informing future research and maintenance conditions. Thank you for your attention. I will be glad to hear your questions.
Center. Any questions? Is it interesting? Okay.
Efficacy from Korea University. I have a question regarding the benchmark. You said you couldn't compare like from machine to machine. I couldn't quite understand. What is it about?
We couldn't compare from benchmark to benchmark software. So each benchmark gives different, has different measure process. So one benchmark software could give a result for the same machine, would give a result of 4,000, a score of 4,000, but another benchmark would give a score of 700. We can't compare these two numbers between them. We have to compare between different moments in the measurement. So if in the beginning it was 4,000 and then it was 4,100, it means we have, but from the same benchmark, it means we have some increase in the performance of this system which we have to investigate. But eventually we had the decrease in critical factors, which are explained in the article quite specifically, because these benchmarks measure a lot of features from these CPUs.
But then using the same benchmark, you'd be able to compare, like, say, same spec machines.
Exactly. For
machines.
Exactly, yes. For the same machine and the same benchmark, you can...
Not the same machine, the same spec of machines, you'd be able to compare from one to the other.
Same spec of machines. Yes, it's true. Yes, you can compare.
Understood. Yes.
Thank you. Any questions? Let's have time for one question.
I'm Yoshiki Yamaguchi. I'm from the Shibari Institute of Technology. And I have one pretty simple question. So do you have any specific reason to choose i7 6600U as your research content?
Yes, we had a number of reasons. One reason was convenience. We had it available in our workshop, and we had a very precise history of the background of the system, so we knew exactly how many hours it had operated, and we were able to use this in the mathematical model. And also it was possible to find new components, because this is the hard part in small businesses like where we operate. It's hard to find these BJ chips brand new. Usually they are used, so we don't know their background. But this one, we were able to find enough new components to perform our testing. And finally, it's a very popular component which went through some time in the industry already. So a lot of information are available, and it's a CMOS component, which means that we can apply the methodology that we already have about aging and measurement of EMC. So this is the main factors that we chose this one.
Thank you very much. It's really clear.
Thank you.
Okay, so any questions? Is it interesting, or we can discuss offline since the time. Okay, so thanks again for the presenter about his work.
Thank you.